All right, so welcome to the second lecture of Introduction to Quantum Field Theory. I have rather good news, and I'll tell you first something else. Slightly okay news, good news. I have recorded the last lecture, and the sound was okay. Someone already noticed, and it's uploaded now on our webpage. There's always the link to the current session. You won't get anywhere if nothing is being broadcast, but you can always reuse the same link, and some people have actually made use of it. And then there will be here a growing list of recordings. I still don't encourage you to stay away, and it's more interactive, but of course, there are circumstances where you have to miss class, I understand. And so we have this opportunity, and I think that's great. Now, the very good news. Yesterday, someone had this idea. We moved the exercise sessions to Wednesday to not collide with solid state physics. But guess what? Now we're colliding with plasma physics. Was that your idea? There was a question, couldn't we have a second exercise session? So both Tuesdays and Wednesdays. But of course, you can't just pull an TA out of thin air. So I pulled him from the ground floor, and we have Lucas Holland probably joining the team, and he'll offer a second exercise class. So we have the Tuesday and the Wednesday days. You can choose, it's the same thing. And now it's about the time. The Tuesday is almost equal, 12 for this and 13 for this, and it's of course not the exact same people. And we'll have to pick one. I can't pull another person out of thin air. So either it's going to be this or this. For now, I'd say the morning session, 11 to 1, but it isn't really decided yet. But we'll have two, that's the good news. And make use of it now, where you can discuss in smaller groups much better than in a big one. These are the announcements. They're really, yeah. So if you remember, we were trying to unify quantum theory and special relativity. And we were not guided by any experiments or anything. We didn't want to reproduce any measurements, any data whatsoever, just come up with a theory that is at least self-consistent, something that mathematically works. And then we can worry about whether it describes our world or some fantasy universe. Just does it work? And the guiding principle was something that worked for non-relativistic quantum theory, namely to start with the dispersion relation. So here, instead of the Newtonian thing, we have the relativistic one. This one. And then replace these quantities E and P by operators, so the correspondence principle. So E is replaced by a time derivative, and P is replaced by a spatial derivative. And then you have an equation for derivatives. You act with them on some wave function. You solve for the wave function, and this wave function is supposed to give you the probability amplitude of finding the particle number. X, here this thing is your random variable, and then you have a time evolution, and that's that. So we did this, and there were already two questions right from the start. Shall we use this equation? Then we get a second differential equation, second order in time derivatives, because there's E squared. And that's different from what we are used to in normal non-relativistic quantum mechanics, where the Schrödinger equation has only one derivative, one time derivative. And we were happy with that because it determines how many initial conditions do you have to give. And if it's second order, you have to give twice as many. Not just the wave function at the initial time, but also the time derivative of the wave function. Basically, what's the change? So either this, or we take the square root. But if you take the square root, we have a square root here. This is not square, the sum of squares. So this will be, in fact, have to be Taylor expanded, and then you have infinitely many x derivatives, and that ends up being a non-local equation. So we stuck with this second order time derivative. Okay, what doesn't matter. We'll deal with this later, and we ended up with the Klein-Gordon equation. This is the box plus m squared c squared over h bar squared, all acting on this wave function by construction. Let's say equal to 0 if there's no potential. The box means the second order time derivative minus the second order space derivative. It's the wave operator. So this, you get this term, is the wave, this part is the wave equation, and has these propagating function there, solutions. In fact, we're really dirty. If there is a potential as well, then we would have to add it before taking the square, so it ends up underneath here. Does that make sense? We'd have to take the square root and add v, take v on the other side, square it again. So if there's a potential, you have this equation. The potential sits underneath, and the potential may depend on x. And then you get a right-hand side, and that has some things in there. So there's a v squared from the square. And then there is another term that is linear in v, and it probably looks something like this. It does, the details that don't matter, it's just saying there is some. And that would be our current naive proposal for the unification of quantum mechanics and special relativity. It's called the Klein-Gordon equation. And if you just say outside this room, give me a Klein-Gordon equation, they give you that term equals 0. So it will be more specific Klein-Gordon equation with potential. And if you're used to this, then we refer to the first thing, the free Klein-Gordon equation. So if there's 0 on the right side, we call it the free. And it looks really good because it contains both constants. It contains h bar for quantum effects. So we expect there to be quantum physics in there. And it contains c, the speed of light. So we expect relativistic effects to be there. Schrödinger equation didn't have the c, it didn't know it. No way that c could be a bound if it's not in our basic equation. So, but here this looks good. And we still didn't know what this psi is. In the Schrödinger case, the non-relativistic case, we have a density which is the square of the psi, absolute value squared, so psi times psi star, and that has a meaning. It's the, because that was the probability amplitude, this is the probability density of finding your particle. It's squared, and it tells you how likely is your particle here and there. And that made sense because this thing is always positive or 0, because you know that's the absolute value of some point. It could be 0, but it can never be negative. For any x and t is positive. And that's one thing. And the second equally important thing is that the integral of the density over all space doesn't change with time. So the time derivative of this thing is equal to 0. Why is that important? Anybody? But
So that nothing leaks out.
exactly. If this is the probability of finding your particle, the probability density, this is the total probability, and if that wasn't conserved, you'd lose your particle. Right? If this is, So it's some number that doesn't change, so we can normalize it. That's what you do. You'd say it's 1, so it's 100% finding the particle anywhere. And this, if this suddenly drops to 90%, where is the thing gone in 10% of the cases? Doesn't make any sense then. So it only makes sense in the Schrödinger case if this is a conserved quantity. And so it only needs to be globally conserved. Locally, of course, it can move. The probability moves around. So this is described by this continuity equation. It's the time derivative of rho. So it can change. The rho itself can change at a certain location. But then there must be a current moving the stuff away. So this is J. Next. And so this, I have to write down, this is Schrödinger, right? This is what we're used to. Schrödinger is the same as non-relativistic. This is how I'm using the term. It's not really the same. Here I mean the standard. We have this interpretation, and that makes sense because this is 0 and you have this. And now we want to see if the same thing applies to our new relativistic quantum mechanics. And it doesn't. So you will show in the first problem set, by the way, very embarrassingly, there was a typo in the most important equation for you, where in the homework it says, take the expression or the charges and the currents from the lecture notes. Now they are wrong. There was a 1/c² missing. It's updated. And if you download the lecture notes now, it's all good, but it was wrong yesterday, embarrassingly. By the way, the lecture notes are really a living animal. Of course, I keep adding sections, but if I find typos or something and makes sense here, I change it. And so that if something has changed, the files have version numbers now. So now it's a V2, version 2, and then if you've downloaded only one without the V2, then you have to update yourself. So then you will show for the non-relativistic case that this, together with this current, J of x and t is minus IH bar to M, and then psi star dx psi minus dx psi star psi. So these two things together satisfy this continuity equation if the psi satisfies the non-relativistic Schrödinger equation. But this rho and this j doesn't satisfy this equation if that psi satisfies now a completely different equation. Obviously, right? How could it? So, however, there are other things that are that you can put here and there, so that this is satisfied using this equation. And the change now is only up here in this row. So for Klein-Gordon, for relativistic, you have rho of x and t is I h bar 2mc². This is the c² that was missing. Psi star dt psi minus dt psi star psi minus v of x mc² psi psi. And now this current here and this density satisfies the continuity equation if you use the Klein-Gordon equation. Yes.
Jim, where does that come from? Just very shortly.
Oh, where does this come from? You try it out, right? You want something that is sort of a square.
Well, what is the definition of rho in general?
There isn't any. It's up to us, right? We're looking for something that is conserved. in the chapter on symmetries, this is the main thing, you're looking for conserved quantities. And then if this is a field theory, there's two different kinds of conservation, right? There's the local conservation law. Things can move, and then you have it's expressed in an equation of this type, space and time derivative minus sign. And this object has the interpretation of the density of the stuff, and this is the current of the stuff. You know, in electrodynamics, you do something, you just take Maxwell's equations and you rewrite, and then you end up with something of this sort. And you don't know what this is here and there, but you have a structure like this, time and space derivative minus sign. And you say, okay, well, then I call whatever's here the energy density, and this I call this the Poynting vector, the energy flux. And that's how you identify them. So I'm looking for an equation that has this structure, and then I give this a name, call this a density. You know, I have a problem finding the right words. I'm calling it density. I'm tempted to call it charge density, but what charge? It's just some stuff. I have called it something in the notes. Sometimes call it stuff. I call it, yeah.
So it just has to satisfy the.
Because it has the structure. You give this an equation, yeah. And you give this an interpretation. And how do you come up with this? Yeah, that's not really obvious, right? You don't really guess this immediately, but you know how it worked in the Schrödinger case. So you want something that's quadratic. It should also be a real quantity, first of all, because probability. What does that mean if it's complex? So the wave function, we assume it is complex because there are i's here right from the start. So it's all complex. So you have to have something quadratic, and one is with star and one is without. Then Schrödinger was first order in time derivatives. Here you have a second order. So if one is explicit, then inside here needs to be a second time derivative, and it is actually there. And you fudge it together and you try it out, and then you see that it is. There's no really. That's why I gave you this rather than saying find it. Okay, so good. Now we have a beautiful equation with H bar and C in it. We have a continuity equation that holds. So this could be our probability density of finding particle at position x at time t. Oh dear, it could be negative. What does that mean now? Is it really so bad? Yes, it is. If it's negative, a negative probability density just doesn't make any sense. Maybe it's easy to fix, but unfixed, it doesn't make any sense. So we have to learn a bit about this. When is it negative? Why is it negative? How do we deal with it in order to fix it? So we're moving on to work with this here. And see what we get and what's wrong and how to fix it. Do you have any? This is the, yeah.
I haven't heard this lecture, but I already heard there's something called antiparticles. I mean, there are antiparticles. Am I too naive into thinking that this might be antiparticles, like negative?
No, you are ahead of the time, right? You're exactly steering in the right direction. There are going to be antiparticles. I never know how to present the stuff, because you could in the beginning take away, I guess you're supposed to take away the punchline in the beginning. This is our learning goal, and then everybody knows where we're going, and you can follow really, really well, and there's no surprises, no confusion, but it's also boring, right? If you have a book and there's a murder and this is now a German class rather than physics, then we have this novel, and I tell you, so this is the book and the murder is X or something, and now we go about and read it and say, look, he's already behaving strangely. It's just no fun. So yes, this is where we're going. The negative things is supposed to be an antiparticle, and all the trouble that we have is that in this equation, there is built-in pair production. You know, relativity has two effects. It has this speed limit, which will work, and we'll see this first. But then it also allows magically for the creation of particle-antiparticle pairs, and this is the first sign. But
Sorry for
you know,
taking away your question.
so pedagogically now you know where we're going, but forget it for the story. But anyway, it's just an hour, and then you'll all know. I want to play with this, and we'll start with the free particle. This partial waves, the simplest thing. And then always go like first the non-realistic, and then it changes to the realistic case. So it's the free particle 1.4, I guess. It's 1.3. The particle. So we have these equations that we're doing. We want a particle of definite energy. So take a particle of definite energy. E has a wave function and has this form. So the psi of x times t is a psi of only x times e to the minus e I e t over h bar. Note, this is a capital psi with a line underneath, and this is a small psi without the line. Different letters, but you'll also be able to tell from the argument. And why does this have definite energy E? Why this form? Because it is an eigenfunction of this operator. So E was replaced by I h bar dt. And if you act with this on here, you have the exponential, all the stuff comes down, minus I and h bar get killed, basically that's why they are here, and only the E comes up. So this is an eigenfunction of the energy operator. So that tells you it's in state of definite energy E. So we'll make this ansatz. And if I plug this thing now in the Schrödinger equation, then you know what you get. You have this minus h bar squared 2m psi, the little one, prime, equals b psi. It's, you know, this is Schrödinger equation. And the solutions are psi of x. It's a harmonic oscillator equation. This on the other side with a negative, so it's an really oscillating thing. We use exponentials to write it. So e to the I something, the something I call t. P is really just the shortening of square root 2m e over the h bar I put explicitly. Are you following me? So you might follow, right? Let's do one more step. This is psi prime equals minus 2 and e over h bar squared psi. This is your harmonic oscillator. This is the frequency. This is the square of the frequency. So I take the square root out of this and call the square root p. Forget the h bar there, put it explicitly. So that's the solution. Of this is one of them. It could also be negative, the minus, the other frequency, e to the minus IPT over h bar. And then arbitrary coefficients a and b. So this is your solution. Why did I give this combination this name? Because this object now is an eigenfunction of the momentum operator. So p is minus I h bar dx, and if I apply this to here, then again all of this stuff comes down, and the thing that sits here is the eigenvalue. So this is the momentum. So that's why it gets the name momentum. So that's our solution. Just to remind you. How does this look like in the relativistic case? Then, as we call so it's free particle, there's no potential. We have, we have the box, right? But the box came from, I'm going back and forth here. If I write it as minus. You see, the equation that we had was e squared equals c squared p squared plus m squared c to the 4. Then we went to the differential equation, and now I'm plugging this thing in, so I end up with the e again. So the equation that I'm getting is e squared psi of x is equal c squared and then come minus h bar squared dx squared. So it's just prime plus m squared c to the 4 psi. It's fine. Thanks. So this is the Klein-Gordon equation with this ansatz.
Sorry.
Yeah.
I feel like the solution we have for the non-relativistic case might be wrong because there is not an x dependency.
Yeah, that's true. Thank you.
The wave doesn't move at all.
What's wrong? Why are you not? What's wrong with you guys? Don't be too polite. This is I don't know. I mixed up my times and spaces. So this is what's wrong. Thank you very much. Yeah, we have the x derivatives, the differential equation x. All right. So this is now the new equation. Second order in that term. And if I solve this for psi double prime, let's say this goes here. Oh dear, and this goes on the other side, so we have minus 1 over h squared e squared over c squared minus probably m squared c squared psi. I've divided by c squared. It goes here and 1 and 2 powers drop. Then this here, this there. All is right. And so this is again the harmonic oscillator that we had, except for a different frequency there. Or it's a wavelength really, wave number. So our psi Klein-Gordon is a constant a e to the I. Now this says I write capital P x h bar plus e to the minus I p x over h bar with e is the square root of this. The h bar is explicit again, so it's just what is in there. P squared over c squared minus m squared c squared. Like we're so dirty. That's the momentum in the new case. Does it look good? If it really wants to be an oscillation, so the I is here, this needs to be a real number, then the energy needs to be big enough. So this term needs to be bigger than that term. So for a good oscillating solution, the E, so we need E to be larger. So E squared over C squared needs to be larger than this, m square root and MC squared. What does that mean? Why does suddenly E need to be bigger than MC squared? Yes.
Because that's the rest energy.
Yes, and E,
Like E is the normal energy.
oh,
and
the
so
total energy, exactly.
Yeah.
So the difference between the two is the kinetic energy. If there's free particle, there's no potential. So you have to have more energy than your rest energy. You can move, then you have a little bit more even, but the rest energy. So it's completely natural that you see this. So you have to have at least this energy. So if I draw a picture, an important picture, you have no potential, and then the lowest energy you can have, this is the energy of the particle. The picture's more interesting if you have really a profile for the potential, but we don't have anything yet. But the lowest energy that you can have is sort of gapped by the mass. All I'm going to say. So that's a free particle. Now, it is a wave. It is some phase with, how does it look like? It looks like the psi, the t and the x is a constant. It has e to the minus I e t over h bar, and then comes this plus or minus. So it is of this form, plus or minus I p, whichever p, the little one or the big one. It's this. So it's a function of t, a function of x, and it's a complex thing. It's, it's the real part is sine, cosine, so you can maybe draw this. So the real part of this looks like this, and it moves. So in x, it is this shape, and if you let time go, it moves in one or the other direction. Do you know? So, and then this is supposed to be a particle with definite energy, E, and definite momentum, P, this P. How fast does this profile move? I just want to know whether you know the answer without doing computation. You're given E and P. You have a particle, think very classically, right? So you have a particle, free particle, energy E, momentum P. How fast is the particle? This is even school physics, yes?
Like P divided by M.
For example, exactly. So the mass of this particle, so the speed of this particle is p divided by m is one way of figuring it out. How fast does this profile move? Well, what makes sense? What would make sense? How fast does this move? Just do it. Tell me. Say V. Exactly. It's yeah.
E divided by P, like I remember for the.
Right. How do you figure this out? So if this moves, it means if you look at a specific value and see how it goes, how this moves. So a specific value means the whole function is constant. It's just e to this. So this exponential, exponent needs to be constant. So set this equal to a constant, whichever you prefer, depending on your choice. You're somewhere here, and then differentiate this equation. So, but with respect to t, and we have minus I e, t by t is 1. Then we have plus or minus I p x dot divided by h star equals 0, and solve it for x dot. Throw away all these i's, and you find what you say. X dot is equal to e divided by p plus or minus, really, depending on where we're starting. And we call this the phase velocity. Because it's this wave is the phase of the zone. The phase of the zone. It's E over P. What's E over P? E is P squared over 2m, right? Over P takes away 1. So we have P over 2m. That's already looking bad. So it's a half V. So the phase of our wave moves at half the speed of the particle that wave describes. This is not at all important, but it's kind of curious, I guess. It just means that the phase velocity has no meaning whatsoever. It's just not physical. And also the rho, the probability density here is a constant. this is just artificial, you don't see anything, the particle is everywhere equally likely, there's nothing really moving there in the probability amplitude, so in the probability density, this is a constant for this kind of. So, all I'm saying, this thing's unphysical. And we found we have there. Now, what is the phase velocity of our relativistic free particle? Is it also half? So here I should write none. This equation holds for both. This is non-relativistic because of here. And here I'm using the same phase velocity, E over P, but I'm going to use the P that we have here. So this is equal to energy over square, right, square root. Square root squared over c squared. I'll write it. Squared c squared. Now I will multiply numerator and denominator by c because I want to compare it to c. So upstairs I have a c, and downstairs inside I have a c squared. So I have a square root. I'll do it the other way around. Sorry. If I can replace E or P, I replace P, I want to replace E, just because to be in line with my lecture note. So this is C squared, P squared, plus M squared, 4 over P. Now we have everything in terms of P rather than fine. And we can pull out the C. So we have P squared plus M squared, C to the 4, P minus C. And the number in front, bigger, smaller than 1? Bigger, right? Because of this extra term. If P is huge, then that doesn't matter. Then we go to C. But if it's small, then it's bigger than 1. So the total thing is bigger than C. And if P goes to 0, the whole thing blows up.
But it's c squared, right?
Where's the C squared?
In the very end,
No,
Take a square.
not because it has to be a.
in the square root.
This is a C to the.
Yeah.
Oh, because yes. There, thank you. Right, it used to be there, it's here now, in this one, right. The function looks like this, if the P is here. It approaches C, but it blows up there, so this is my phase velocity. So it's really faster than, I could live with 1/2 of the speed, it's just half, fine, it's weird, but okay. But I don't want this to be, so this is not just unphysical, this is terribly unphysical. The description is in terms of a wave, if that's working out, if this is all working out at all, and the description is in terms of wave that goes like nuts, really fast, for a particle that is hopefully, I'm looking for my speed limit. So we can't look at the phase velocity, we'll have to look at the other thing. The group velocity. What's a group velocity? We have a group of these waves, we make it a little uncertain, we don't have a clear momentum, and a clear energy, so we superimpose solutions of this kind, and then we shape some wave function. So we add these things together with different wavelengths, and so there's a point where they all add up and where they average out somewhere else, and then it looks like this, right? So that's how we like it. But it's made out of things in between. So the I don't know the envelope, the Einhülde of my wave has a certain profile, and that moves with the group velocity, while everything inside here moves with a phase velocity, with their own phase velocity. Every momentum has a different phase velocity, right? Because it depends on P. So they rearrange inside, and as a shape it goes with the group. So what's the expression for the group velocity? Well, it's not
It's
the quotient, it's the derivative, right? So you take dE by dP, or same thing, it's d omega by d k, when you remember how you do it. You write this sum, like the Gauss, or some profile for the amplitude, so you're adding in the different partial waves. But this is really the prefactor. Where's my wave? So here, you add terms, they all look like this with different p's, and you have an a that depends on p, and you add the things, and then you expand your amplitude function and Taylor expansion around the p where it's concentrated. That's how you end up with this thing. So this derivative is from the Taylor expansion of the amplitude function, dividing it into the exponential, do the same reasoning as you did there, and then you end up with this simple equation. That's one way of doing it. Another way of doing the same thing, so this is method one, and method two is you just divide the current by the density. The J that we have divided by the rho. Because the current is the density of the stuff times its velocity. Right? So the current is the density times the velocity, or you divide the current by the density of the velocity. So let's try this out in both cases and see if this is more physical than what we found here. So we found this, and now we do the group velocity. On relativistic. So V group, method one, V group is dE by dP. This is d by dP of p squared over 2m, and if I differentiate, the 2 goes away, so this is p over m, and that's m times v, just to make it really exciting, so it's v. So the group velocity is really the velocity of the particle. Shall we do the other thing? Yes. So we need rho. Rho, so what's my wave function? My wave function is a e to the I minus I e t over h bar plus I p x over h bar. I'm taking for definite. To be specific, I'm using the plus sign. And then the rho is psi, psi. So the phase goes away. This is really the a squared. And the j, what's the j? That was minus I h bar 2m d psi dx psi minus e x psi star psi. So this guy, the derivative is I p over h bar, right? And so the first term minus I and I goes away, h bar goes away, so we have p over 2m. The first term is p over 2m, but the second is the complex conjugate of this. what's my minus sign doing? Well, it's the same, but the complex conjugate has a minus sign there, so I get minus IP over H bar. And with this minus, I get a plus, so I get two of them, and then I forgot the amplitude. It's A squared. So now you don't know what I'm doing. This is that term, this is minus IP over H bar, and the result is this, and you cancel the two. Next time I'll do that. J is equal to A squared P over M, P over M was V, so it's A times V. And therefore, the group, which is J over rho, the A squared goes away, is V. Works. All right, so this wasn't exciting. Now the exciting part is to do the same thing for the relativistic particle. And method one, V group is the derivative vector P. E is square root C squared P squared plus M squared C to the 4. And then we have this thing 1 over 2 square root. The 2 always goes away because of this inner derivative, and then we have a C squared E. Right? And the inner, and the 2 is canceled the 2 from there. And what's that? This very much looks like what we had over there. Let's cancel one C again. So this is equal to E, one C to the back, the other C in there. So it's E squared plus M squared C squared. And this is now the other way around. So if this was bigger than this is smaller than 1, so we have, right? It works. There's our speed limit. I wanted to make a simulation, but we didn't have the time really to discuss this, but I encourage you, if you like computers and visualization stuff, to do the following: superimpose some of these, just a few of your partial waves, particles with definite, a number of particles with definite momentum and energy. I erased the solution. Something, it looks like this, but here the P and this is the E of P, the relativistic one, and draw it, the real particle thing, and let it move in time. You should see this thing. You should have, and then you speed it up, right? So depending on P, you let P go, then they should go wild. Actually, no. If P goes down, then they go wild. But the whole thing moves relatively slowly. And you can compare with the other thing, you see the factor of 1/2, so it should be a fun picture. You see the unphysical phases, particle waves moving, and then you have this loop, and our speed limit is built in, so that's a good thing. Now, where am I? Let's do the second method. The second method is not going to bring anything new. It will also be group velocity less than C, but I think I want to compute the density and the current as well. So method 2, rho, this was this complicated thing. It was I H bar 2 and C squared, don't forget that. And then psi dt psi minus dt psi minus, we have a free particle, so we don't need to this thing. Is there a minus sign? No. Now, we have the time derivative rather than space derivative, so we're gonna get minus IE over H bar. We cancel again everything. This will get the same term, so the two goes away. So we have E over C squared times A. Yes, after work, and J, well, J is literally this expression. And it's just that one with a capital P. So we are going to get A squared and the capital P over M. And does this look right? M, where's the M here? There it is. And the C, I'm not sure whether or not I like the C. There's no C. Is there a C? This is a hard formula, I have to tell you. Well, I guess I like the C. Now, V group is a J over rho. And then we have A squared P over M divided by this. So MC squared over A squared, and that's what we had. So this is C squared P over E, and that's the same with the derivative. So this is equal to C squared P over C squared P squared plus M squared C to the 4, same as above. Okay, so on the
It would be A squared, or
yeah, we
in the upper right.
yes. Okay, so let's summarize what we learned. We have our Klein-Gordon, the Klein-Gordon equation that we reconstructed, the way they did it, produces solutions that look like these non-relativistic waves, and they have this built-in speed limit. The phase velocity exceeds c, it's always faster than c, goes like crazy, but in a group of particle waves, the particle behaves nicely, and we have actually succeeded in constructing a theory with a speed limit. Wonderful. On the flip side, this rho, and that's why I wanted to compute it, this rho has a problem. If rho, if you now have it in a potential, so if there was a constant, it could be even non-constant, but let's say constant, it's not constant potential, be zero, not equal to, so constant non-zero potential, then I'm gonna write this into this dirty line here. It's important, small enough for it, actually. Then the rho, we can actually read it off from there, because we said the V is always subtracted from the E. When we can substitute it. Rather than doing the whole computation again, which you may want to do, we end up with this thing. So this, in a simplifying formula, says if the V is larger than E, that can be negative. Then is negative for d less than d0. Well, I'm really trying hard to destroy the whole thing, because how could the energy of our particle be less than the potential? This looks like here. So this is 0, then we have a potential. That is up here. That's our V0. And here's the mass, right? Let's say this thing is mc squared. And so our energy we learned, so that we have a solution, should be larger than mc squared. This is the rest energy, so our total energy will be bigger. So in this case, I mean, if E is less than V0, then that's negative. It's never going to happen, right? I'm doing something to really deliberately break the thing. I mean, why would I have to draw? Why do I draw attention to something? It could be negative if this happens, if this never happens. But it sometimes happens. So we could do this. We have a piecewise potential, a piecewise constant potential. Let's do this thing. So here's V0, and there's 0. And now we come in with a particle of this energy. So that's my energy line. That's what this thing is. This is E, and that's perfectly okay because I'm larger than my rest energy. And then it hits this wall. What's that wall? The wall is a force, right? So the step in the potential is a force. There's a huge force acting to the left here. You know, we gain energy, so there's a force in this direction. The force is only acting at this location, so it's an infinitely large force, which performs this amount of work. If the particle comes on this side, this force performs exactly the V0 of work. There's a huge, so but it could happen, right? You have a particle coming, and then you hit it with a strong force. That's what I'm doing. And now I'm saying, if that's the case, that the E is less than V0, then something is weird, and rho is 0. So we could talk about many examples where everything works out and it's really nice. But here, I'm steering towards a problem. I really want to tease out the problem. So I'm constructing something where something can break. I need to test the theory, and I have to really try to break it. And that's the place where I could. Rho should never be negative. No, I'm trying to make it negative. All right. So next chapter is on the potential step here. We had a little success story with the speed limit. This revealed the possibility that rho is 0. I pointed it out yesterday already. Now we see it again. And now there's where it fails. The failure is the particle production. So if you want to tell us what happens there, what do you predict is going to happen there with that force? You want to just guess something wildly? Just guess, yeah.
Okay, like rho gets negative, so we create an anti-particle.
Yeah,
Just a guess.
exactly. So there's this strong force.
The force
It doesn't only hit the particle badly, it produces anti-particle pair or something. We don't really see that in. That's the problem. We don't know exactly what it is, but it's something creative. What is the it's just different. Oh. Once you start with water, then. Yeah, it's good. And four. Potential. Step. And. Nine, the Klein-Gordon Klein's paradox. So we are interested in exactly this situation where the potential is zero somewhere and then it's goes to a constant b zero and the particle that we have is lower energy than that. So this is the issue. We can discuss many things, but we'll say this. And also, well, that's not really important. That's only for the realistic case. Do I have to remind you of how this works for the non-relativistic case? I mean, I have 30 minutes, I have to, what happens in the non-relativistic case? We're solving the Schrödinger equation, here and there, piecewise. So just the result. When x less or equal 0, you have psi of x is a equal to IPx for the thing that goes in. You have a plus b equal to minus IPx for the stuff that comes back. And the p is square root 2me as before. And then for the other side, you have something else. Since the energy is smaller than this, it's not really an oscillation, so it's an exponential e to the alpha x plus e to the minus alpha x, where the alpha is the square root of 2m b0 minus e. And then we have constants c and d. That's how this thing looks like. For the non-realistic case, I haven't derived it, but you told me you knew it. Now we argue that the wave function should at least be bounded. So this growing exponential, we don't want to give this any definition at all. So we set the c equals 0 to have this bounded, and then we have the oscillation here, and we have a damping there, and then you can calculate the transmission and reflection coefficients. So first you compute the currents, J incident, J reflection. Do I need to do? So this is the same expression for the current that we had applied to the incident term. The reflection term is this, because it goes the other way. And the transmission doesn't even have that shape, so that's 0. So you compute these things. And then the ratio, the reflection coefficient, let's write it out. Reflection coefficient R is J reflection over J incident. And since the momentum is negative, the current will have a sign, it'll be negative. If I want a positive reflection coefficient, I really take the absolute value here or a minus sign. So that just takes care of this going the other way. This is the positive number, and you calculate it. What do you find for this setup? 1, because the poor thing has to come back. The force is so strong, it has to come back. No way. There is nothing propagating inside. It can tunnel a little bit, but not through. It's not a potential barrier. And then the transmission coefficient T is chance divided by incident, and that is 0. Okay, fine. So that was just recalling the non-realistic case. Now we do the same for the do this more slowly for the relativistic particle. Um. Our wave function psi of x is a e to the I capital P x plus b e to the minus I p x. For x less than 0, and it's psi of x c e to the I p prime of x plus d e to the minus I p prime of x, where b, the normal one, is e squared over c squared minus n squared c squared, this thing, and the p prime is just offset by potential square root b minus b zero squared over c squared minus n squared c squared. That's the solution. Piecewise, we have to still patch it together, but that's what it is. Here, the patching in the non-reducing case I just haven't done, but it's a relation between the A and the D and the A and the D, and in this quotient, these drop out. Can we set 1 to 0? Like here? There's no exponential growth. Can you still set 1 to 0? Do you have to set 1 to 0? What are we doing? I don't want 4 constants. Yes. D, why?
Because there's no.
Oh, a reflection back. It's not called reflection because you are in this region. You mean there's no incident from the right. There's nothing coming in from the right. So you don't want anything going to the left on this side. So that's why he proposed to take D, set D to 0 on basically physical or like experimental, like our choice to set it up that nothing comes in from the right. I'll set this to 0. However, this thing is not the guy that's going to the left. Because it has a negative phase velocity, but the phase velocity isn't anything important. We have to look at the group velocity. And funnily, the group velocity of this guy is positive, and of this is negative. So this is the one going to the right, and this is going to the left. Let's try this out. So we go J. Didn't we have this somewhere? Here, let's just stick there, right? Because it's the same computation. Just with the P. Here I didn't have the plus minus. I'll stick the plus minus in again. So we have plus minus C squared P prime, because we're on the prime side, over E, what is E? E is P minus V zero. That's my guess. There.
Dividing by rho in this case, right? Like this. I think like dividing by E only comes about because you divide by rho. Right?
Yes, and the row was somewhere here, which is also gone now. The row is still here. It's this thing, right? The row is E minus V. Now we're in a potential, and this is V zero. And that ends up in the denominator. So this is the right expression. I just don't know if I have to derive it. Because I want to get to the punchline and skip the boring steps. This is the computation that we have done right here with, sorry. I'm writing different, this is not the J, this is already the quotient, I'm sorry, that's why you're pointing it out. This, there's some J, and after having the J, then you have the group velocity. This is with the division. Yes. We're doing the same computation as before, except for now, there was a constant, now there is one, and we have to replace E by E minus E0, also in here. So if you spell this up there. And now, since the V0 is so big, it's bigger than that, so the denominator is negative, switching the sign. So if you have the upper sign, the upper sign was this. So this is the result for the minus ET over H bar plus or minus IP prime X over H5. This is the way the upper sign gives this upper sign, but with the upper sign, this thing is negative because of this funny denominator. So we're tricked there for the first time. We think, that's why I talked about phase and group velocities. You look at it, and I, before thinking about it, did the same. This is to the right, the left. No, it isn't. This is to the right, this is to the left, and this is to the right. So what we're going to do is set this to 0 because we don't want anything coming from the right. Same setup, but it's a different term. All right. And why is that again?
We're defining it that.
Well, why is it reversed? Why is this to the right? How do you see that this is to the right? You compute, I know you have it here, you compute the group velocity rather than looking at the phase velocity. Looking here is looking at the phase velocity. So this is now the thing, now we have to patch this together, right? Matching condition. At x equals 0. So this has to be the same as this. If you put x equals 0, it's wonderful. So exponents go away. So a plus b equals t. This is the continuity of the wave function, but also the derivative has to be continuous. So we differentiate once, and then we get an IP. We get an IPA minus IPB equals minus IP prime D. And now A is what comes in, and I want to solve this for E and B. So the I goes away. This is the place where we can like skip ahead. This is solving a system of linear equations. So the B is P plus P prime over P minus P prime times A, and D is 2P over P minus P prime times A. So in order to match these waves up at the step, you have to have this relation between the constants. And now the currents J in. Really, do I have to? I just erased it. It is A squared P over M, if you remember. We did this. The J reflection is the P coefficient, and then the same P and the M, but a minus sign, because it's a minus P in the exponent, and the transmission is the P, and it's the P prime. It's probably more complicated. Is it more complex? No. Is it over M? What could it be? What else could it be? That, right? Yeah, so easy. You agree? I mean, I'm not doing every step, but makes sense. And here I'll plug in this. Or it's to the quotient. Minus J reflection over J in. This divided by this with the minus sign is just P over A. And B over A is this. So you have P plus P prime over P minus P prime. That's squared. Let's wait until we scheme, and then this is J trans over J in. And now it's this divided by this, and then we have the D over A, but also the P prime over P, and P over A is this, so we have 2 P over P minus P prime squared times P prime over P. We square this. So it's P squared, one away, and the one with the prime, nice and symmetric, so P minus P prime squared. There it is. Really, it's the same expression as in the non-relativistic case, except for now these are capital V's because of the other relation to the energy, and the primed, it's an opposite sign. So compared to the Schrödinger, here's the plus and there's a minus. And this means the numerator is bigger than the denominator, so this is larger than 1. So there's more stuff coming back than we shot at the step. And this, what is this? I forgot the minus sign. Where did I forget my minus sign? Because there is a minus sign. Because here is a minus sign, right? Is there a minus sign?
Yes.
Because this is coming from here. And then it goes there and there and there. So this is negative. And if you spent a minute, you would find R plus T is equal to 1. This is bigger than 1, this is negative, and this is so negative that it takes away what is bigger than 1. So we come in with 1, but then it's not just a bit going back and a bit going through like we're used to, if the step isn't high enough, if it isn't too high. But here we are under the step. And more is coming back, and some, well, what does it mean? It's negative is going there. Blue, I don't know what to do. And some is going there to the right, because this is what it is with this thing. Something's going to the right, but negative is. So the total probability is conserved. The total probability is conserved. This is what we had. The integral, we had a conservation equation. So we did know that even for the Klein-Gordon, the total integral, this is conserved. The time derivative of this is 0. Nothing is lost. but locally, it makes something weird. It's now overly probable to find something on the left and less than probable to find it on the right. So now I destroyed it. There you go. Now it's broken. We have a continuity equation. And so this in graphical terms, you have some object, a little later, it moves. And the area underneath is the same always. But if you wait long enough, you have a weird situation, then it suddenly grows here and then it goes there. That's what it does. I have a picture for you. You fell asleep. You just stand by. Oh, low energy, that's fine. State is a negative energy state. Bear with me. Act. Let's see. Sorry for this. Now, let's start slowly. I have the relativistic case, non-relativistic case. I do this, I thought it was a German course. And this is the barrier. It's higher than what you see, so there's no coming in. And I superimpose these waves to have a Gaussian, and then it bounces there. Here, the wiggles is because it interferes with itself on the way back. There's just the exponential decay and easy, right? What I'm drawing is the wave function itself. The wave function is a complex function. So the picture here is the value that is drawn on this scale is the absolute value of the wave function, and the color is the phase. So red is a real number, very fast. So somewhere there's a real number, positive, and then there's the cyan blue, which is the negative and in between. That's how I draw it. Now, the density, which is the absolute value squared. So it really is the same thing, just squared. So the absolute value squared is this. It looks the same. It's just, first it was a Gaussian, yet it's the square of a Gaussian, it's kind of a Gaussianism. Boring, nothing. I did it anyway. And for the Klein-Gordon case, the wave function looks like this. And that is now the interesting thing. Something's coming in, and it does wiggle as before, but there's someone produced on this side. And it's a positive function because I'm plotting the absolute value of psi. It's a complex number. What else should I do? It's not even negative, it's complex. Yes? And there it is. There's a little thing coming in and a big coming out, and a big little coming in. That's what's happening. This is a solution of our equation. We haven't done anything wrong. We just came up with an equation, solved it for a special case of the potential, and this is coming up. Yeah.
Phases also change a lot quicker in the potential side. Can you explain? Or is that not intuitive?
Probably when you think about it. So at the moment it's counterintuitive. What does it mean? If so, there's e to the I px. If this changes quickly, it means you have the colors here are the values here, so the phase. So the many colors means it changes quickly, so we have a large momentum. That means there should be a lot of kinetic energy. I mean, in general, this if your potential and if you have a state of certain energy, then here the colors will change quick and they're less. So
Why?
why is it here? Because here there's this potential, but kind of backwards. But you have to think from the top now. So what do we have to think? We have E minus V 0 squared needs to be
Okay.
bigger than M squared C squared. So we take the M squared C before, that is what's underneath the square root. This is my P. And now we take the absolute value. I mean, we take the square root and it's absolute value here, and there's just this MC squared. And what does it mean? That the difference between them needs to be larger than MC. So if this is my potential, this is E0, where does this E need to be? The difference between E and V needs to be large. So the E cannot be there, right? It can be bigger by this or smaller by this. So there's a little MC here, and the E can be in this range. It cannot be smaller than this. So in this range, I have really something going on there. And then maybe above again, but okay. So, and in this phase, there's also this distance. So probably I have a solution that is close to here rather than close to there. So this is a large number, and that's giving you the fast speed. Yeah. It's not super relevant, okay, but I'm glad that I drew this picture. So in this region, you have to be larger than this so that you can shoot actually with something. You couldn't shoot anything if you don't have enough energy to have a particle in the first place. But then something strange happening if you don't get too close to the thing. So if the force is really strong compared to your energy, the potential is really, so don't go, here's something happening. And then it goes through and comes back, and more is coming back, then you send in and something's going through. So there's your particle production. We'll make this more explicit in a second. If you don't have enough extra, like over you, it's not going to produce anything. If you're up here, then nothing happens, won't even enter. But if there's enough, it creates it. And so now you've been waiting for it. You want to see the density. And this is now the honest density, the one that I tried to draw here, that evolves in time. It's conserved, the total area is conserved. Here, this grows. This is negative. So, but here it's more probably to have it than there. I don't know how many times I've said it. I'm starting to get bored. On my own lecture, the total thing is one. And what do we do with this? Before, what's happening? So before we hit the step, we have one particle moving to the right. After, we have more than one particle going to the left, and one particle also going to the right, but with a negative charge, with a negative probability, with a negative rho, with the negative of this stuff. And finally, now I can call it a literally charge, and you may think of electric charge. This thing has the opposite charge of this. If I have had a positively charged particle coming in, then I have created something with negative charge and positive charge, so they equal each other out. It's zero. I've produced nothing really in terms of charge. It's conserved. But there's a particle, and this carries the negative charge there and there. This is our pair production. So we have built into the equation the particle production, which would be a wonderful thing, because this is what, and I think it's amazing that it's in this equation somehow. The problem is that we can't really deal with it. The formalism isn't right. Why? If I ask, how, so here, this is now my rho. Some rho of x. Let's say we fix t, and that's that. How would you, now you know there's positive and negative charges. Now I ask you, what's the probability of finding your particle in a certain interval? What would you answer? Since you don't know how many particles there are and what their charges are, your answer is ambiguous. You could say, okay, well, in this interval, I have this area, so I guess this is one particle with that probability. But wait a minute, it could also be a little bit more particle with additionally the other charge in it, or you can't distinguish between one particle is more likely, or there are more than one particle, and then there's a negative somewhere else. So the formula isn't right. It's not the multi-particle thing. But doing relativity requires that. I think it worked perfectly. This is exactly the end of the story. Next week, we will develop a multi-particle formalism from there. So that's what we need. This version of relativistic quantum mechanics isn't a good formalism. It's a start. If you don't go in this region where you break it, I really tried. There are other places where it works. You don't have these hyperdense convective energy, and you can make predictions with this. But there's also this particle difference. So that's why we need it. Good. Questions? Wishes? I will figure out when the Tuesday exercise class will be. I would say 11 to 1. But I'll confirm this because I have to look at who voted. I want to make as many people happy as possible. I still realize I can't do everything, but all right. Thank you.